This is ELC131, Circuit Analysis 1, and this presentation is on series RC circuits. Impedance is symbolized by the letter Z and is measured in ohms. The unit symbol is the Greek letter omega. Impedance is the opposition to alternating current. And impedance is a combination of resistance and reactance, where reactance is the frequency-dependent opposition to a sinusoidal alternating current of an inductor, X sub L, or a capacitor, X sub C. Mathematically, X sub L equals 2 pi FL, and X sub C equals 1 over 2 pi FC. Now let's look at the phase relationships in a series RC circuit. In a series circuit, the current is the same for all components, both in time and magnitude. So we'll use current as the reference for a series circuit with respect to time. Now, the current through and the voltage developed across a purely resistive element happen at the same time, as illustrated in Figure 3. However, you recall from our discussion of capacitors that current leads voltage by 90 degrees in a capacitor. Therefore, the capacitor voltage happens 90 degrees after current and the resistive voltage, as shown in Figure 4. Now, it's difficult to illustrate the phase relationship between VC and VR by sketching the sine waves as we did in Figure 5. So we represent this phase relationship using a vector diagram. Figure 5 provides us the voltage vector diagram for a series RC circuit. Again, I and VR are our references, so we put them at 0 degrees on the vector diagram. And VC happens 90 degrees after VR and I, so VR is at negative 90 degrees on the vector diagram. Now, Kirchhoff's voltage law states that in a series RC circuit, V source equals VR plus VC. However, since VR and VC do not happen at the same time, we have to add these together as vector quantities, where VR and VC make up the two sides of a right triangle, and V source is the hypotenuse of that triangle. So mathematically, V source equals the square root of VR squared plus VC squared. This is Pythagorean's theorem. And with these series circuits, we're concerned about the angular difference between VR and V source, which is called the phase angle, and is represented with the Greek letter theta. Mathematically, theta equals the inverse tangent of negative VC over VR. We have to include a negative sign with the value of VC so that we will obtain a negative value for theta as shown in Figure 6. Now, let's discuss the impedance of a series RC circuit. Now, recall from our rules of polar math that when we divide polar quantities, the magnitudes divide and the angles subtract. So the opposition to current, as seen by a capacitor, X sub C, equals VC at negative 90 degrees divided by I at 0 degrees, which gives us a value for X sub C at an angle of negative 90 degrees, as shown in Figure 7. And the opposition to current of a resistor equals the resistive voltage at 0 degrees divided by current at 0 degrees, which gives us some value for resistance at an angle of 0 degrees, again as shown in the vector diagram of figure 7. Now, impedance is the vector sum of R and X sub C. Again, R and X sub C make up the two sides of a right triangle, and impedance is the hypotenuse of that triangle. So the value for impedance is calculated by finding the square root of R squared plus X sub C squared, again Pythagorean's theorem. The phase angle of the circuit can be calculated using these values of R and X sub C by finding the inverse tangent of negative X sub C over R. Again, we have to include a negative sign with our value for X sub C so that we will return a negative value for theta as shown in figure 7. So let's look at the analysis of a series RC circuit. So referring to the circuit of figure 1, we have a source voltage of 14.14 volts peak at a frequency of 1 kilohertz. And this source is connected to the series combination of a 1 microfarad capacitor and a 180 ohm resistor. And the first step in our circuit analysis is to find the value for X sub C, capacitive reactance. X sub C equals 1 over 2 pi FC, which for the circuit of figure 1 gives us a value of 159 ohms. Impedance is the square root of R squared plus X sub C squared. For the circuit of figure 1, the impedance is 240 ohms. And the phase angle of the circuit is the inverse tangent of negative X sub C over R, which gives us a value of negative 41.5 degrees. Now, as you recall from the discussions of trigonometry in ELC131A, we could calculate the phase angle by finding the inverse sine of negative X sub C over Z, where this is the inverse sine of the side opposite to theta divided by the hypotenuse, or we could calculate theta using the inverse cosine of the adjacent side R over the hypotenuse Z. And the impedance vector diagram for figure 1 is shown in figure 8. Now we look at the voltage calculations for the circuit of figure 1, and again point out that all these calculations are RMS quantities. So I've converted the 14.14 volts peak to 10 volts RMS. So the current in the circuit is Vs over Z. 10 volts divided by 240 ohms gives us 41.7 milliamps. The resistive voltage drop, I times R, is 7.51 volts. And the voltage across the capacitor is I times X sub C, 6.63 volts. Now we can also find the phase angle of the circuit using the voltage values. Theta equals the inverse tangent of negative VC over VR, which gives us negative 41.4 degrees, the same as using the impedance and, the resistance and capacitive reactance values from the previous slide. The voltage vector diagram for the circuit of figure 1 is shown in figure 9. Now we don't have to do this, but I think it's always a good idea to check our math by finding the vector sum of VR and VC by again finding the square root of VR squared plus VC squared, just to ensure that we did not make any math errors in calculating current or the voltages in the circuit. So we see again that by finding the vector sum of VR and VC, we end up with a value of 10 volts. So we can feel confident that we did not make any mathematical mistakes.